Welcome to our webcast on the determination of polyaromatic hydrocarbons from aqueous matrices utilizing solid phase extraction and non-halogenated extraction solvents. I'd like to introduce our speaker for today, Jim Fenster, who's an application chemist at Horizon Technology.
Good afternoon. Very happy to be here talking with you today. I will briefly discuss the following in terms of this presentation. What motivated us to do the work, descriptions of the equipment used in these studies, followed by a discussion of the methodology and a discussion of the work that we did, and then the conclusions. Polycyclic aromatic hydrocarbons, PAHs, are ubiquitous and are components of fossil fuels such as crude oil, gasoline, and coal. They are also present in products made from fossil fuels. Atmospheric emissions are dominated today by anthropogenic activities of man, and these emissions closely map population centers globally. Given the carcinogenic nature of these compounds, the U.S. EPA and the European Union, as part of its European Water Framework Directive, has listed these as hazardous priority pollutants. The priority assigned to these compounds makes any new developments in their testing of particular interest to the international community. Today's discussion will focus on the extraction of these compounds from aqueous matrices. As all of you are aware, water samples range from extremely clean samples all the way to heavily particulated, dirty samples, depending on their source. Today's environmental testing laboratories are faced with the entire spectrum of samples from clean to dirty, and trying to use standardized methodologies to treat incoming samples the same way. Current methodology today includes liquid-liquid extraction, continuous liquid-liquid extraction, and solid phase extraction. All of these technologies have benefits and drawbacks in terms of impact on laboratory safety and also sample throughput. For instance, liquid-liquid extraction is very simple to do, so training is minimal. However, it uses great volumes of solvents, takes time, and is problematic with emulsions commonly occurring. Continuous liquid-liquid extraction is time-intensive and greatly impacts the amount of results a lab will generate in a given time. SPE recently has gained great acceptance because it is efficient, uses smaller amounts of solvents, and can be automated. SPE discs in general are gaining wider acceptance in environmental labs because they are able to be used with large volume samples and also can be used with dirty, highly particulated samples. In all of the existing methodologies, methylene chloride is the solvent of choice because of its excellent solvating properties across the entire polarity range of compounds, and also because of its relatively low boiling point, making it easier to concentrate extracts faster. It is for this reason historically that DCM has become the universal solvent used in labs everywhere. However, methylene chloride is a known carcinogen, and many government and safety authorities are starting to limit its use. So a need has existed in the analytical community for solvents and methods that extract as efficiently as DCM does, however with more safety for the lab workers and our environment. In 2009, Friedrich Verres and his group at IWW published a paper summarizing their studies in trying to develop the methodology to extract PAH compounds using SPE discs and non-chlorinated solvents, in this case acetone. In their work, they looked at using acetone as the eluting solvent when using SPE discs, and also developed their methods to work with highly particulated samples as well as clean water. The group was able to generate a method that worked very well However, given acetone's hydrophilic nature, also extracted a lot of residual water into the final extract. It was necessary to treat their extracts because of this with large amounts of sodium sulfate to dry their samples prior to analysis. Our goal for this work was to build upon the work of the various group started at IWW and develop a new method for the extraction of PAH compounds using a non-halogenated solvent system other than acetone. This new methodology would also allow us to use another technology to dry our samples prior to GC analysis, and also develop a method that works for clean water samples as well as samples with high sediment loads. I would just mention quickly that sodium sulfate is the method of choice today to remove water from samples. Its mechanism is chemical by absorption of water from organic extracts. Typically, sodium sulfate is added to extracts and they are filtered through filter paper where a column is constructed using a long-necked funnel fitted with glass wool. In order to get the best results, the sodium sulfate is usually pre-treated. Some of the common problems associated with the use of sodium sulfate as a drying agent are listed in this slide. Primarily, they are sodium sulfate has a finite capacity for water. Emulsions tend to be very difficult to deal with and are common with sodium sulfate. The use of sodium sulfate tends to be fairly operator dependent. Typically, long filter times are experienced due to gravity flow. You must condition the sodium sulfate before use, and they need to be heated in the oven. And the sodium sulfate must be pre-washed with solvent before use. And after being used, it is considered a hazardous waste and must be properly disposed of. And maybe the biggest drawback of the use of this material is the fact that it will also selectively absorb compounds of interest. This slide comes from some work done by J.T. Baker showing some of these base compounds in a mix of semi-volatile compounds actually absorbing on the sodium sulfate desiccant. In evaluating extraction efficiencies, we sometimes focus on extraction technique and concentration technique and don't think a whole lot about the technique we use for drying our extracts. Horizon developed dry disc technology in order to create a membrane-based platform to dry environmental samples. It is based upon the physical separation of water from organic solvent. The membrane is constructed from Teflon and has a pore size of 0.1 micron. It uses a vacuum to rapidly pull solvent across the membrane and at the same time retains water on the other side. It is very quick and easy to use. It works best with organic nonpolar solvents. Polar solvents like methanol or solvent extracts with acetone higher than 30% will carry water across the membrane and will not work. It was for this reason that it was important to develop a methodology that did not exclusively use acetone to elute with. For this work, we used the Steedex 4790 automated extractor using Atlantic brand C18 extraction discs. When working with clean water, we used a 47 millimeter disc holder. For particulated samples, we used the same setup, but used the fast flow sediment disc holder fitted with a 1 and 5 micron filters on top of the 47 millimeter C18 extraction disc. For drying and concentration of samples, we use the dry vap concentrator system that is equipped with dry disc technology. For 1 mil endpoints, we use the 0.9 EV tubes, evaporation tubes, and for the 10 mil endpoints, we use the solid tip evaporation tubes. Reagents and materials are listed in this slide, as well as the analytical instrumentation. In this case, an adjuvant 6890 GC with 5973 mass selective detector. The GC used the Phenomenex Zebron ZB 5MS column, 30 meters by 0.25 millimeter ID. As mentioned, for particulated samples, we use the fast flow sediment disc holder with 1 and 5 micron filters. This slide shows a particulated sample being processed through the 4790 extractor. In the bottom left-hand side of this slide, you'll see the various stages of sample processing on the system. If you look at the fast flow sediment disc holder after extraction, in this case shown on the lower right-hand side of this slide, you will see that the bentonite clay did not pass through the filters and kept the SPE disc from clogging. Depending on the amount of sediment in your sample, extraction total times for extraction will average anywhere from between 33.5 minutes and 36.5 minutes. This slide shows the methodology we employed and the sample treatment prior to processing. All samples were pre-treated the same way and also processed the same way, whether they were clean, distilled water samples, or samples with clay added to them for particulate load. The samples with bentonite clay were extracted using the fast flow sediment disc holder and the 8-second rinse technique on the extractor. The 8-second rinse technique was necessary because of the increased surface area of the pre-filters used on the fast flow sediment disc holder. The 8-second rinse technique resulted in more solvent, acetone and hexane, being used to extract the disc. The Speedex 4790 is controlled by the Envision platform controller. The 47 millimeter and the fast flow sediment disc holder Envision techniques are listed in this slide. After method optimization, it was possible to develop a single method, which is shown here, that works for clean and dirty samples both. Extracts were dried and concentrated on the Horizon dry vap. Conditions for 1 mil endpoints are shown in this slide. After reaching endpoint of 0.9 mil on the dry vap, the heater and UV tube were rinsed with solvent and brought up to a final volume of 1 mil and quantitatively transferred to the GC valve. Extracts were dried and concentrated on the dry vap. Conditions for 10 mil endpoints are shown here. After reaching a finish at 5 mils, the dry vap heater and UV tube were rinsed with solvent and brought to a final volume of 10 mils in a graduated cylinder, and 1 mil was quantitatively transferred to a GC valve. After dry vap software was used to set the T5 value in the software to a 2-minute nitrogen sparge after heater shutoff. After the 2 minutes, the system final extract volume of 5 mils was achieved. Recovery ranges from 82% to 99% for the 1 mil endpoints, and all around 100% for the 10 mil endpoints were achieved. The effective concentration was studied by preparing solvent spikes. 30 micrograms of PAH standard mix were put into EV tubes containing 30 mils of acetone, hexane mix. The mix represented the mix of solvents used to elute the SPE discs in these experiments. These measured recoveries of solvent spikes at 1 mil endpoints and 10 mil endpoints. As you can see in this slide, the 10 mil endpoints showed little losses when compared to the 1 mil endpoints. 10 mil endpoints showed less losses of the more volatile components in the PAH mix. The differences were greater for these lighter end components because of their volatility. This is due to the sparge times being much less for the 10 mil endpoints compared to the sparge times for the 1 mil endpoints. 10 mil endpoints had a 2-minute sparge time, while the 1 mil endpoints had sparge times ranging from 30 to 45 minutes. The same data set in the previous slide is shown here graphically with these bar slides to make it easier to see the greater deviation on the lower, lighter end compounds. We next extracted clean water samples made from distilled water. This slide shows recovery results from this data. So clean 1-liter DI water samples were spiked and processed on the 4790. Comparisons were made between samples extracted with 5 hexane rinses versus 3 hexane rinses, and results were the same for 3 rinses versus 5 rinses. This was slightly more loss. There were slightly more loss again using the 5 mil rinses with the 1 mil endpoints of the lighter ends because of the additional sparge times needed to bring these to their respective endpoints. However, the heavier end components had slightly better recoveries. This slide again is showing the previous slide's data in a graphical manner. So it's much easier to see the relative differences between the hexane values with 3 hexane rinses versus 5 hexane rinses. And as you can see, the lower end, like naphthalene and acetylnaphthalene, has larger losses associated with the 5 rinses that we used on the 4790. This is because using 5 rinses created more extract that needed to be concentrated, and the sparge times on the dry vap were much, much longer on the 5 rinses versus the 3. This slide is showing recovery data from extractions of particulated samples using the fast flow sediment disc holder. Recoveries of PAH from these samples range from 73% to 90%. For samples processed with 2-minute air dry times, and samples with 1-minute air dry times, recoveries range between 79% and 92%. The same data is shown here graphically for highly particulated samples. In these experiments, the air dry times of 1 minute and 2 minutes were compared. And using the fast flow sediment disc holder, it is necessary to use an air dry time that gets rid of most of the residual water. However, care must be taken that too long an air dry will also decrease recoveries of the more volatile components like naphthalene. Finally, this slide shows a comparison of methodologies. So previous extractions using DCM as the main extraction solvent were compared to acetone-hexane mixes. The same data, again, is presented graphically here. SPE methods were compared using DCM versus the new solvent system of acetone-hexane for extraction of these PAH compounds. This data shows that acetone-hexane solvent system extracts these compounds as efficiently as the DCM solvent systems used in previous methods. So in conclusion, I just want to state that we have developed and demonstrated an efficient method for the extraction of PAH compounds from water samples using C18 extraction discs, and a method that employs non-halogenated solvents. This work builds upon the earlier work done at IWW, but this time uses a solvent system that allows the use of dry disc technology to get rid of residual water. There are many factors affecting the efficient extraction of PAH compounds. Many of these factors are associated with drying and concentration of extracts, like the amount of time that nitrogen gas flows over the samples, and also the length of air dry times during the extraction. We think that each of these factors can be further optimized in future work. I just wanted to say thanks and acknowledge some of the previous work done by Friedrich Zares and his group at IWW, as well as Julie McKettrick, Chemical R&D Group at Horizon Technology, and Bill Jones, the Director of Chemical R&D Group at Horizon Technology. I also would like to thank all of you in the listening group for taking the time to listen to this talk, and I'll be happy to entertain any kind of questions you may have at this point.